Okay. Hello. Wait. Did everybody get the notice that it's recording? Okay. Hi, everybody. Today we have a session on basic AI enemy design with Fouad Abou Harfoush. Fouad, I'll leave the floor to you.
Hi, everyone. Welcome back. How is everybody doing? Hope you're doing well. I'm excited for this session. It's going to be interesting. Okay, can everybody see my screen? Yes, sir. Okay, perfect. Tamam. Okay, so it's not wait anymore. Let's start. Sorry, I think somebody has their mic open. If one of the mods
could please mute your mic. I'm trying to mute you, but it's not working.
Okay, yeah, the sounds. Sorry about that. Okay, so that little interruption. Let's start. So, okay, no, it's happening again. So sorry. I don't seem to have.
Who is it? It's no one.
Okay, I don't know if Rafiq you can hear me, but I'm gonna please ask you to mute. I'm not sure why I can't mute you myself. Are we able to mute this person?
Agreed.
Yeah. Okay, perfect. Everybody's muted. Great. Sorry about that. So in today's session, we're going to learn how to make a very simple, basic enemy AI. And by AI, I don't mean the current sort of trend of AI, just an enemy that you would see in a platformer game, basically. So first off, whenever you're making something, we have to, or don't have to, but it's generally a good idea to list out the requirements for what we need. So I'm going to open this question up to you guys. We want to create a simple enemy for our platformer game. What are the requirements for that? What do we need to make? Feel free to type in the chat. Behavior patterns. Okay. Yuduki visuals. Yeah. That would be pretty good for myself, but I can't teach you how to do that, unfortunately. Well, the question is, what are the requirements? So how do we get from having no enemies, no logic for our enemies in our game, to having something that we can use to build an enemy? Hitboxes. Okay, so those are some good answers. So here are the requirements. So first of all, ideally they'll need to have health and be able to take damage from the player or other things in the environment. They will also need to damage the player when the player touches them. Now, you don't have to do it this way, but this is just the way we're going to do it for our example. Third, we need to be able to define states and transitions between those states. So we need to define states for the enemy and how that enemy transitions from one state to another. So kind of how you're saying behavioral patterns, but very much we're going to see how to make the simplest version of creating behaviors. So let's define some of those states. We want an idle state where the enemy or entity just stops all movement and can flip from left to right depending on the situation. We want a patrol state. We want the enemy to be able to move from left to right, stopping at walls and ledges. We want a chase player state. So if the player gets into a certain range, we want that enemy to start chasing them. And we want to define a death state for when they run out of health. So how can we create these states? How can we define them? How can we define the transitions between them? Well, this is where the concept of a finite state machine comes in. So finite state machines, they're just a model that define, its definition is, it's a model composed of finite states and the transitions between them. So from that definition, we can infer a couple of things. You can only be in one state at a time. You have to have a finite number of states, so you can't have infinite states. We just have a discrete number of them. And we have transitions between these states. So this is the conceptual definition of finite state machines, but what do they actually look like on paper? So this is an example of a finite state machine diagram. Just looking at this, you've probably, if you've been messing around with Unity for the last couple of weeks, you've probably seen something similar like to this. If you've done any animations, so this is how the animator works, exactly like the animator, 100%. So it's very similar. The animator is basically a finite state machine. It has states and transitions. That's basically it. So here, we're just trying to figure out how the design of this enemy that we're going to create. So we have our idle states, and as you can see by the arrows, the idle state can go to either this is the patrol state. So after waiting a few seconds, it will start moving left and right. And then if it detects a wall or a ledge while it's in the patrol state, it will go back to idle. And we have the chase state. And the chase state, you can transition to it from either the idle or the patrol, as long as you detect a player. So you can see it's just a very simple diagram of defining what the states are and the transitions and how we transition to them. What's the actual trigger for transitioning into the states? This is generally a good idea if you're doing finite states to always, do it on paper or like inside of a software, to just draw these states and their transitions and connect them, because it will really help you, define all the things you want to create. And of course, here we have the death state, which can be transitioned to from any state. So whether you're an idle, chase, whatever, if the health of this enemy drops below 0, it goes into the death state. Okay. Okay, this is all nice and well. Do I have any questions so far about what we just talked about? Because now we're going to move more in towards how we implement them. For now, we're good. Awesome. Okay, so we understand now conceptually how we want to design this enemy. But how do we actually do that? What are the things we need to know to actually do that in Unity? So there's two concepts that are pretty important for us in this case. We need to learn about inheritance and function overloading. So if you've done any programming, especially any object-oriented programming in the past, you probably are familiar with these. But for those who are not, I'm going to explain. So let's first talk about inheritance. So inheritance is the process of which one class acquires the properties of another. So here in this example, we have three classes. We have the animal class, and we have the cat and the dog class. So the animal class, we define a property called the fur color, and we define a function that just returns to us what that fur color is. So our cat class here, for example, inherits from our animal class. Now, what does that mean? What do we gain from that? Basically, our cat will also have access to the fur color and get fur color method and property. So it inherits those properties from the animal class. And it adds its own method, which is the meow class, void meow. You can see we also have like a dog class, which defines its own method, but also inherits from the what we call parent or base class, the animal class, the fur color and get fur color method. So yeah, we usually call the class that you inherit from parents or base, and the classes that are that we are inheriting into the child or derived classes of that parent. So yeah, inheritance is a really nice tool that we have in specifically object-oriented programming of structuring our objects, our classes in a hierarchical order. And we're going to see why that's important for us when we move to the example. Okay, one more thing I want to talk about before we move to actually showing you code and how it's going to work is function overloading. So the simplest way I can define a function overloading is, okay, let's say you have a derived class like we just talked about. But in your base class, you want to define some function that the child classes will be able to implement on their own and change. How can you do that? So let's say here in this example, we had like a method in the animal class called make sound, right? Because all animals kind of can make a sound. So it makes sense that we have a method that's all the child classes inherit called make sound. And instead of defining a meow or a bark, we just take that make sound method and we change it in the child. So how do we do that? This is what function overloading is. So when we have a function that we want to implement in an inherited class, we use what's known as a virtual function. And we do that using the virtual modifier. So if we look here at our example, this is from a parent class. And the parent class defines a method called public virtual void enter. And in this method, we take a start time, we note down the start time, we set a Boolean for the animator, and then we're calling a method called do checks. And this method has this special modifier called virtual. All this modifier does is it lets you, if you're inheriting this method, to override it and change it in the child class. So if we look here to our right, this is an example of where we're overriding this method in a child class. We call public override void enter. So the override lets us know that, hey, this is a function that was virtual in the parent that I know exists, and I want to change it. I want to add on top of it. So in order to do that, we call base.enter. This base.enter is important. Basically, what it means is very simple. We're just calling the same 3 lines of code here these three lines in the virtual function in the parent class, this is where they get called in the override. And as you can see, after calling these three lines of code, we're doing some extra stuff after that. We're setting a velocity, setting its idle time over to false, and calling a method called set random idle time. We're going to see what these methods actually do in a second. Are we clear so far? Do you have any questions before we move on? What if we remove the base dot enter? Good question. Basically, you'll still be able to call the enter function as if you were like calling it from the base class, but those the lines here in the so basically everything in the virtual method will not be called when you call it. So base dot enter basically just calls everything within the base method, and if you remove it, you just won't have those. You'll just have whatever you defined in your override, which you might want in case you have like a very special case where you don't want to do the stuff in the virtual method, you just want to do something completely different. Does that answer it? Okay, awesome. Okay, so let's move to Unity. And thank God I've already opened Unity, so we don't need to wait very long. Let's see here. So this, guys, is it's part of the project that we've shared with you on GitHub. This is the development for branch. And as you can see, we have everything we've worked on before, the UI, all the logic. We can't see, or you can't see my Unity? Okay, hold on. Let me stop the screen share for 1 second. How about now? You see the slideshow? Oh, it might be because the slideshow is full screen. Okay, awesome, awesome. Now it's working. Perfect. Okay. So yeah, as I was saying, this is just the same project we've been using throughout this entire course. It's on a different branch. It's called the development for branch. If you want to see everything we've worked on so far plus this session, this is where you want to go. And as you can see, the only thing that we've added here is these little guys, which we've called blue beetles because that's what they look like. And these blue beetles are some very simple enemies that we've built using the finite state machine method that we've talked about. So first, let me just show you. Some massive glare in the background. Okay, so as you can see, we have this little guy. He's walking around from left to right. So when he hits this wall here, he's going into his idle state. And yeah, this is a very, very simple one. He doesn't actually have a chase state. He just walks around left and right like your basic Goomba from Mario. But if we go further into the level, we can find this little guy here who will actually start chasing us. He sees us. Well, maybe he can't because he's on such a short ledge. Yeah, look at that. Okay. Okay. So how do we do this? Let's look at our code. So first, if we look here at the hierarchy, we have this blue beetle. This is just a parent for the entire object, and this is just a good tip is to just always separate your objects in a as best you can. So here we have this parent class, which is just a transform. Inside of it, we have an entity. this entity has a script called Blue Beetle entity, which we're going to see now. It has a rigid body, 2D, a box collider, 2D, and a damage box. The damage box is just so when we hit it, we take some damage. It's the same script that we're using for the spikes. Underneath that entity, we have the sprite. So this is just the sprite on its own. And generally, it's a good idea to separate your sprite into a separate object in case you want to manipulate the sprite in any way. Will the recording be available somewhere? Yes, of course. The recording will be available on YouTube like all the rest. Oh, look who just joined. Okay. We have another object here called checkers, where we just have a bunch of transforms. And see, these are just empty transforms that we're going to use in our entity to detect walls, detect the ground, to check for the player. We're going to see all of this once we enter. What we're going to do now. Why is the damage box a separate script? Couldn't you make it on the same Blue Beetle script? Good question. So the reason it's a separate script is because I don't have to tie it to the rest of like it doesn't have to be tied with this entity specifically. I can take this damage box component and put it on anything else, and it will work as a box that if I run into, the player will take damage. So it's just a good idea in general to make your components as small as possible. As we say, single responsibility. We say that's the official term. Like, try to make them have the smallest amount of responsibility so that you can reuse them in modular ways like this. Yes, exactly. That way we don't have to rewrite the script over and over again, but we can just put this component on anything that has a box collider and it will work as a damage box. Okay, let's get into our entity script. So before we actually look at how our finite state machine is constructed, I'm just going to show you how these enemies are how I've decided to sort of tackle making these enemies. So this is our Blue Beetle. You can see here, this this way of writing things, where after the class you open this the two dots, and you have another class. We've seen it before, right? We've seen it. Let's see, actually, if I can. Let's look at our spike trip here. We've seen this way of writing it before, right? When we wrote spikes, 2 points mono behavior. This is how you inherit things in C#. So this means that the class spike is inheriting from mono behavior. And if we go back to our entity, here we can see that the Blue Beetle entity script is inheriting from entity, which is another script that we've written. So let's take a look at that first. Let's take a look at the parent before we start looking at what the child is doing. So here we have public class entity. It's deriving from mono behavior. It's also deriving from something else called iDamageable. So let's put a pin in iDamageable for a second. I'll get back to it at the end. But just know that it's inheriting from these two things right now. Mono behavior just gives us access to all the Unity functions that says add components. You should know this at this point. So here we have a very long list of properties. Let's just walk through them. We have a public finite state machine. So this is our state machine. This will drive the states and transitions of our enemy, and we're going to take a look at it in a second. We have something called entity data, D_entity. So if you were here last time, I'm going to go into it. If you were here last time, this this entity data script is a scriptable object. So it's just defining certain properties that we might want to reuse for all of our enemies, which is why we've made it a scriptable object. Like max health, what the max health for our enemy is, what is the distance of our wall check, what is the distance for our ledge check, what is the radius for our ground check, etc., etc. We have other things here too. We have a rigid body. We have an animator. After that, under the checkers header, we have these 4 transforms, which we've seen here, right? These are these 4 objects that we're referencing here. And these transforms, we're going to be using them over here. So these 4 functions, what they're going to do, so let's take a look at one of them. Let's take a look at the check wall front function. What it does is it returns the result of a physics 2D raycast that goes from the wall check position in the transform.right direction, taking in we take the entity data wall check distance as the distance of this raycast, and we check it against the ground layer mask. So let me quickly explain what a raycast does. So here, basically what we're doing is we're going from one point, we give it a distance, and we give it a direction and a distance. So we're defining this vector that is just shooting to the right. And we're telling it, check if you've hit anything that belongs to this ground layer mask. So layer masks are just a simple way for us to define, sorry, where is it? Over here. It's just a way to define what layers a raycast can detect. And you've seen layers before, right? It's what's over here. So you can see this entity is part of the enemy layer. And if we look at our layer, we've assigned them the player layer. And we also have our ground, which has the ground layer. So we've separated these objects into layers so that we can more easily detect them in these ways using raycasts and other methods. So basically what this function is doing is it's launching a raycast and telling us if we've hit, if we detect ground, which for our purposes is the ground and also like all the walls. It's all the obstacles. So it just tells us if there's a wall in front of us, basically. I'm not going to go over them all in detail. If you want to sort of check them, you can do that on your own. You can download the project and go over them. But basically check ledge is just checking if there is a ledge, or if there's not a ledge, it will return false. Check ground is just a little circle underneath our entity that is checking if there is ground underneath. We use this to detect if we should be falling or if we should stop falling. You can kind of imagine how this goes. We also have a check for the player. We check if the player is within a certain range, because we might want to use that to do some things in our logic. Besides that, what does this entity class have? It has these 3 velocity setting methods, which we just use to set the velocity of our rigid body. It's very similar to what we did in the player for the player's movement. We have this flip method, which just flips the enemy, very simple. We have some gizmos. We're drawing some gizmos here. So if you look, if is it disabled? So now I've enabled gizmos, and you can actually see here the different checks, the different raycasts and checks that we're doing. So this is the ground check that we're doing. This is the radius that it has. And this is the wall check. You can see it's going this direction. It starts where our wall check starts, and the ledge check. So this method, which is called onDrawGizmos, it's similar to like update or start. It's a method we inherit from mono behavior that Unity gives us. And it's just used to draw these like helping lines in Unity so that we can better see what's going on exactly. Besides that, we have a take damage function, which just removes some amount of health and then checks if the health is below 0. And yeah, that's basically everything here. So okay, it can set its movement, it has these checks. How do we actually define the states? How do we go from idle to patrol? That's where our state machine comes in. So let's take a look at our finite state machine class. So here you can see it's actually a special, we haven't seen this before yet. This is not a class that derives from mono behavior. It means this is not a class that you can take and put on a component. It's just a class that you can instantiate at runtime. Not sorry, instantiate, but you can create an instance of and do some logic in it. But it's not deriving from mono behavior. It doesn't have an update. It doesn't have a start. It can't be attached to a component, right? It's just a regular class. It has 2 states, like a current state and a previous state. It has an initialize function, which just takes in a state, sets it as the current, and then calls current state.enter. And it has a method called change state, which takes in a new state, sets the previous state as the current one, exits the current one, sets the current one as the new one, and enters the new state. So this is how we transition from one state to another using this method right here. And this here just allows us to initialize our state logic to enter. Okay, I have a question in chat. I saw in one of the raycast methods on the direction you use transform.right, and in the other one you use vector2.down. What's the difference between transform.right and vector2.right, for example? Excellent question. Excellent question. Okay, so let's see here. Let's see here. If we go to our transform.right, we can read here the little description that it's giving us, and we can kind of understand. So transform is the transform that's attached to the game object. So this is the transform of the game object itself. And dot right means it's the red axis of the transform in word space. So the difference between transform.right and vector2.right is vector2 is constant. It's always pointing in the same direction. It's basically, if we look here, and you can see, if you see this little gizmo here, vector2.right is always going to be pointing where this X is pointing to, right? It's always going to be this direction here. Whereas transform.right depends on the transform's rotation itself. So if this transform is flipped, let's look at this little beetle, for example. So here, it just so happens to be pointing in the same direction. But if we, for example, rotate it like this, you can see this is what transform right will be now. If we take it, it's pointing that way. So that's basically the difference. It's one is constant and the other depends on the transform. Am I lagging? It's a good question too. Muhammad, does that answer your question? Okay. Okay. So let's go back to our finite state machine. So we know how our class, the finite state machine class works, but how do the states work? What are they doing? You know, it's when you enter, we can see already that it's also a class that doesn't inherit from model behavior. And it defines certain properties. It defines a public start time, which we're going to use to know exactly the time where this state started, where this state started executing. And we have a couple of protected properties. Now, what does this protected modifier mean? So it's similar to public and private, right? It's a modifier for a property or a field, but protected, it's kind of like private, but it allows any class that derives from this class to also have access to these fields. So whereas private, if you define something as a private field, you can't access it from anywhere except that same class. Protected lets you access those properties if you're inheriting the protected field. Okay. So let's see what else we have here. We have this method here. So it's different from our other methods. You can already see like the color here is different. We're not calling void anywhere. So what is this exactly? This is what we call a constructor method. So a constructor method is a special type of methods that lets us initialize a class. So when we call, for example, here state, let's say new state equals new state, we can see here that it's asking for an entity, a state machine, and an animation Boolean name. Excuse me. So this is basically what we've defined here. This is what the constructor is. It allows us to create a method so that when you're initializing a class, you have to pass in some properties. And you can see here where we want an entity, which is this class here, which is the base of our enemy. We want a state machine, and we want a string animation name that we're going to use to communicate with the animator as to which animation you want to play. Okay, after that, we have a couple of functions that you can see are all marked as virtual. So this is what we talked about before. This is, we're going to use, we're using virtual here because when we create our different states, we want to override their functionality. We want to give them special functions. So in here, in our enter state, we're taking the start time, we're setting the entity's animator as Boolean value to the Boolean that we're passing in the constructor, and we're setting it to true. And we're calling doCheck, which is just another method that we have here. So this enter method, for example, what we're going to use it for is when we're defining our different states like idle, patrol, chase, we want all of them to have this basic functionality here, but we want to add, we want to add special calls for depending on the state itself. Okay, so let's look at this in action. Okay, we have enter, exit here, just also sets the animation to false. Let's look at where we're using the states class. So here I've gone to our idle state, which you can see here is deriving from the state class. It has some different properties, an idle time and two booleans, one that's called flip after idle, and the other is called is idle time over, which we're going to see how they're used. And it has some state data, which is, again, this is another scriptable object that we're just using to define the minimum idle time and the maximum idle time. So we want, because in our idle states, the common logic that we want all our idle states for all our enemies to have is we want them to have some sort of some idle time, which will be chosen at random. So let's look here. We have a method called public override void enter. So here we can see this is deriving and overloading the method that we described here. And it's taking the base.enter and it's doing a couple of extra steps. It's setting the velocity to 0. So because here we're going to be using this method as soon as we enter into our idle state. What do we want to do when we enter? We want to set the velocity to 0. We want to stop the player from moving. We're also setting is idle time over to false, and we're calling set random idle time. So if you look here at this method, it's just taking a random number that's in between our minimum idle time and our maximum idle time, and it's setting idle time to that. And here in our logic update, we are checking if the current time is bigger than our start time plus our idle time. If yes, we're setting is idle time over to true. And if we go, yes, okay. Yes, that's all it does, basically. This is so it's enters, waits a bit of time, sets idle time to false, sets is idle time over to false, waits a random amount of time, then sets is idle time over to true. Okay, but as you might have noticed here in our idle state here, we're not actually transitioning between states because this is still a class that we've defined that we're going to use as another base class. So this idle state inherits from the state class, and we're going to construct, if we go here, another class called blue beetle underscore idle state that inherits from that idle state. And you can see in our logic update, we're calling the base.logic update, which if I just hit control and I click on this call, it's going to take me here in our idle state, which is just the one that we just saw. So if we go back, if we go back here to our blue beetle idle state, you can see it's in addition to checking if the idle time is over, it also checks if idle time is over, then we want to change the state to our move state. And this move state, we've defined it here in our blue beetle entity. So maybe this is a good time to go back to this class actually and see what it's doing. So why did we even do this? Like, why did we make an entity class and choose to inherit from it? Well, because the entity class is just going to define all the basic logic for our enemy that we're going to use for every enemy, that even if they have like different states or different like special logic, they all will still have movement and the ability to take damage and what have you. So really all we're doing in this derived class is we're defining the states themselves. So you can see here we have an idle state and a move state. And in our start function, we are creating a new instance of the blue beetle move state, passing some values to it, and a new instance of our idle state and passing some values to it, and initializing our state machine to the idle states. So what happens now basically is if we press start, it's going to create these instances and then tell our state machine that we are in the idle state. And so all these methods here, it's going to call enter. It's going to start calling these methods. But where are these methods actually called? Well, if we go to our entity class, we can see here in our update methods, we're calling state machine.currentState.logic update. So this is where we're calling the logic update function of our current state. So if we're in the idle state, this will be this piece of code here, or more specifically, for our blue beetle, it's going to be this piece of code here. So this is called in the update function of the entity. In our fixed updates, we're going to call the physics update of our current state, which again, is going to depend on how you've implemented the state itself. Okay, so let's see. Do I have any questions so far? Is it clear? Is it a bit confusing? Is there anything I can explain in a better way that you feel I haven't explained well? Okay, okay. I'm just going to wait a little bit, see if there's any questions. If there's not, we're just going to keep moving forward. Let's see. Okay, doesn't seem to be any questions. Great, that's great to hear. Okay. So if let's just follow the state logic from the beginning to try and like really trace what's happening. So we go back to Unity. This blue beetle, this entity object has this entity script, this blue beetle entity script. It's going to call start, which is going to initialize the state machine to our idle state. If we look at what our initialize does, it just sets the current state to the one we passed, and it calls enter. So in this case, it's going to call the enter of our blue beetle idle state, but because here we haven't defined a special case for it, it's just the same one here. It just does this. And then in our update and fixed updates, it's going to be calling our current states logic updates and our current states physical. Okay, let's look at the move state. So let's look at here's the move state. So the move state has, again, some properties. 2 booleans, is detecting wall or is detecting ledge. You can imagine what these booleans are actually used for. We have our constructor, which we're just passing in some basically, actually, let me go over this in case this isn't very clear. So this constructor here is deriving the entity, state machine, and animation Boolean name, so these three here, from the parent constructor. So you can see here it's the same way of writing this this inheritance here. So it's inheriting the constructor from the base class. So these three here. This is just so we don't have to write this piece of code again every single time. We just write it this way. Where's the move state? Yep. So yeah, it's defining a constructor which is just taking as an extra to our entity and state machine and Boolean name. It's taking also a state data, which is just a scriptable object with one float property called movement speed. So this is where we get our movement speed from. Let's go back. As you can see, we're overriding three of the methods from the state class. We're overriding do checks. We're telling it set is detecting ledge equal to entity.checkLedge. So if we go to this method, this is what we've seen before in an entity class. This is the raycast that's basically detecting if there is a ledge in front of us or not. So if I go back to Unity and you look at this little raycast here, this is what this is. It's used so that, let's say, if the enemy is over here, it's walking, it gets to this point, it's going to detect that there's no longer a ledge and it will stop. So this is what we're using it for. Back to our move state. We're also checking if there is a wall in front of us using our entity.checkWallFront method, which we went over before. So very simple. We're just setting these two Booleans here. In our enter, we're setting the velocity of our entity equal to the movement speed that we've defined in our state data. And in our physics update, which again, we're calling in the fixed update of our entity, we're again setting the velocity equal to our move speed. So this is the piece of code that actually moves the entity. If we go back, again, what I'm doing here is I'm hitting control. And once you do that and you click on a method, you can go to its definition. So here, I went to the definition of set velocity, which is in the entity class. And the set velocity just takes the velocity, it calculates using a smooth damp and the current velocity using a smooth damp, and it sets the rigid body's velocity equals to the calculated velocity. This is the same exact method that we're using for our player. Okay, so that's the move and idle states. Actually, no. There is one missing thing here. If we go to our blue beetle move state, so here inside our blue beetle underscore move state, which is inheriting from the base move state, we're overriding the logic update for the state. We're saying if you're detecting a wall, or if you're not detecting a ledge, then first of all, I want you to flip after you wait your idle time, and I want to transition into the idle state, right? So this, if we go back all the way here to our little diagram, this is basically this section here without the chase state, right? If we detect a wall or a ledge, we go to our idle, and once we're on our idle, we wait a few seconds, then we go back into our move state. And that's basically it for this enemy. It has these two states, and it just transitions between them. Everything good so far? Question mark? I'm going to assume that the silence is a yes. That's basically how the finite state machine works. That's basically how it works. It just, if you're building a more complex enemy, all you're doing is adding more states, right? So we can actually look at an enemy here. We have our blue beetle chaser, which is just a very much a smaller guy. And if we look at his class, it's basically the same exact thing, except he has a chase state also. And if we look at the logic update in his move state, we have here, this is the same thing we were doing in the other class, but we also have this line of code here, which checks if the player is inside the range and goes into our chase state. So yeah, we're just defining another state. If we go to our chase state here, we again have a logic update. We're waiting a certain amount of time before going back to our idle state. Or if we also detect like a ledge, if we detect a ledge or a wall, we also want to stop chasing and stop. And we're setting in the physics update where this is where we calculate the velocity of our entity in order to chase the player. So we're checking the direction to our player and setting the velocity according to that direction. We're flipping the entity actually, and then setting the velocity according to that. So yeah, this is basically how finite state machines work. They just get more complicated by adding more states, more transitions. Okay, let's see. I have a question. Can we go back to entity for a second? I kind of forgot what was happening there. Okay, so entity is basically it's the parent class for all our different enemies. It's just defining a set of functions and properties that we want to be common for all our entities. So primarily, we have the stick damage, we have the velocity calculations, we have these four functions that define how we our checkers. So checking if there's a wall, checking if there's a ground, checking if the player is in the range. And also it has a state machine, and this state machine in the update method, we're calling the logic update for our current state. And in the fixed update method, we're calling the physics update of our current state. So if the state machine is in a current state, let's say here it's in move, so we've transitioned into move, it's going to be calling the logic update of the move state that we've defined for our entity. And also in the fixed update, it will call the physics update of our move states. Does that clear things up? Okay, no worries. There's a lot of like inheritance and states and transitions, and it's a bit confusing, but once you know how these things are actually connecting, it starts to become a bit simpler. Because basically, ideally, once we've built this entity class, and we just don't touch it anymore, right? We've built our basic logic, and khalas, if we want to define uh, a special logic for our states, we do that in the states themselves. We don't touch the entity class anymore. Okay. Let's see. There's one more thing. Okay, let's see this question first. How does the state change after the first initialize idle method? Okay, good question. So let's look at our blue beetle here. So here in our start, we called state machine initialize idle. So we've entered the idle state. So now the logic update here that's being called is the logic update function that we've defined in our idle state here. So this one, right? This is the idle state for the blue beetle. And if you look here, if the idle time is over, we're calling state machine dot change state to our move state. And if you remember, when we call change state, we're setting the current state to be that new state, and we're calling enter on the new state. So just to follow the logic here, okay, the idle time is over. So first of all, this is where that is being decided, right? We're checking if the start time is bigger than the idle time, and the idle time, we're setting it here, which is called in our enter. So when we enter, we decide, okay, I want to wait 2 seconds. In our logic update, okay, we check, has 2 seconds passed? If yes, then this is true. So now, since this idle time is over, is true here, over here, we're going to switch states. We're going to call change state and go into our move state, which first, let's see, what's the move state here for this blue beetle entity? As you can see here, we've set it to this class. So first, it's going to call enter on this move state. So here we did not override enter. So it's the same one that we've inherited, which is just setting the velocity. And then, we're doing the fixed update, we're doing the logic update, and so on. Did that clear things up? Okay. One more question. Yes. No worries. It's a bit, I understand if you might have gotten a bit lost. So really no worries. But I'm more than happy to answer all your questions. Why is the finite state machine in the constructor of our states, right? You mean this one right here? Yeah. So because we want the state to have a reference, we want our state to have a reference of the finite state machine, because inside of our states, we want to call, primarily because we want to call change state, right? So in our logic update for idle, we want to see, okay, our idle time is over. We want to change states, and the change state is defined in our finite state machine class. So that's why we're passing it. Okay. Awesome. Glad to have cleared things up. Okay. So what does ref do? Where is the ref? If you're referring to this one over here, I'm not going to go into that right now because it's a bit out of scope for this session. But if you'd like, you can look at the documentation for the smooth damp function. So if you write Unity smooth damp into Google, you'll get this documentation, and hopefully it will explain it for you. But I'm not going to get into it now because it's not really the topic we're covering. If you want, you can also DM me on Discord and I'll answer it separately. So okay, there's one more thing I want to cover, which is this eye damageable. We kind of, we saw it at first and we ignored it and moved on. But what is it and why is it a different color? So let's go to our eye damageable class. So if you can see, it's actually not a class. So I just said, let's go to our class, but it's actually not a class. It's an interface. So what is an interface? Let me go back to my slides here. Okay. So an interface is basically, it's a thing which other classes can inherit that acts as a contract for the inheriting classes. So it defines to them, it tells those classes that they need to follow a certain structure. It tells them what they need to define, but it doesn't tell them how they actually go about defining those things. It just tells them, you need to have, in our example, you need to have a function called take damage. How you implement it, the interface doesn't really care. It just says this deriving class needs to have this take damage function. Let's go back to our code here. So this is exactly what we're doing. We're defining a public interface called iDamageable, and we're writing a method. You can see without an actual body, it's just the signature. So all the classes that derive from the interface called iDamageable, I just stands for interface. All of them need to define a take damage function. So why did we do this? Why are we doing this? Basically, because in our game, we have many things that can take damage. Our player, our enemies, I don't know, maybe later on, we want to add like a door, so a static object that you can shoot at and destroy. That's technically, that's taking damage. So that object will have to eventually define a function where it takes a damage amount and it subtracts something. So it needs to define a take damage function, basically. That's why we use an interface, because there are many objects in our game that need to have somewhat the same functionality, but like we don't care how they implement them, we just need them to have it. So here our iDamageable is used for our entity, and if we go to our player controller, it's also used by our player controller. So if we look here, the player controller also has a take damage function, but it's different. It's the take damage function that's deriving from iDamageable, but here the actual body, the actual definition that we defined for our take damage function for our player is different than the logic that we have here for our entity. But this is useful to us because now that we've added entities, let's say one of these enemies runs and hits a spike, we want them to take damage. Ideally, it would be weird, if you saw an enemy hit a spike and it didn't take damage, it might be a little weird. So we've decided that as part of our requirements, we want the enemies to take damage from the spikes. So if we take a look at our spike class, we have on trigger stay 2D. We're checking if the collision is the player, and we're calling collision.getComponent iDamageable take damage 1. So this actually, because here we're comparing the tag to the player, this will only call for our player, but we could do something like this. If I remove this check here, and we just say, hey, when a collision enters, check, get the iDamageable components of that collision and call take damage. So here the spike, doesn't really care if it's a player, if it's an entity, if it's a door, if it's a whatever, as long as it has the iDamageable component, it will call take damage on it. So here, just for the sake of not writing incorrect code, you would probably want to write it like this: iDamageable not equal to null. So here, you'd probably want to write it like this. You want to add a check to see if the collision, if the object that has entered the spike trigger actually has an iDamageable. If it does, then you call take damage 1, which just means give this guy 1 thing of damage. So that's the basics of interfaces and why we use them. So is that clear? That's basically the last thing I'm covering here. So if that's clear, so please do. This is the time to ask all of your questions, if you have any. Okay, let's give it a second. We actually have a couple of new things in this one, in this branch. So, okay, doesn't look like we have any questions. Okay, so that's the session. That's the basics of how you create a very simple finite state machine enemy AI. Okay, I'm going to leave it to the moderators now.
Fouad, thank you so much for joining us. This was a very informative session. I hope it was as great for you as well, for you participants as well. And yeah, I hope everybody has a great weekend ahead. Let me turn off the recording.